would help astronomers look back to a period not long after the Big Bang, when the cosmos was still young, raw, and chaotic. At that stage of the universe, only a few 100 million years after its birth, the first stars had just begun to flicker into existence. These were massive, unstable stars, living fast and dying young. The galaxies they formed were thought to be small, messy clumps of gas and dust, primitive building blocks that would, over billions of years, merge and evolve into the majestic spiral and elliptical galaxies we see today. But when Webb pointed its golden mirrors deep into that ancient light, it didn't see chaos. It didn't see the baby steps of a universe just learning how to create structure. What it saw instead left scientists stunned. Nestled in the depths of cosmic history, only a few 100 million years after the Big Bang, Webb revealed a galaxy that looked impossibly old. Not a scattered, unshaped cloud of stars, but a fully mature spiral galaxy, complete with sweeping arms and a brilliant, organized core. In other words, the telescope discovered a cosmic giant that simply should not have existed at that moment in time. To put this into perspective, think about the timeline. Our universe is about 13.8 billion years old. According to every major model of cosmology, it should take billions upon billions of years for a galaxy to collect enough matter, enough heavy elements, and enough stability to sculpt itself into a structure as refined as the Milky Way. Yet this galaxy had already reached that level of maturity in a fraction of the time, less than 400 million years after everything began. For astronomers, this was not just unexpected, it was impossible. It was like opening a history book on the very first chapter and finding a story that belonged at the very end. Something was out of place, and it challenged the very foundation of how we understand cosmic evolution. Webb wasn't just taking a picture of deep space, it was taking a picture of a paradox. The data suggested that galaxies were capable of evolving at an astonishing speed, far beyond anything predicted by the standard models of physics. If this was true, it meant that the universe had processes, mechanisms, or even laws of nature that scientists had never imagined. It raised questions about the very flow of time in the cosmos, the conditions of the early universe, and whether our most trusted theories had been missing a crucial piece of the puzzle all along. This single discovery was enough to ignite heated debates across the scientific world. Was this galaxy a one-off anomaly? A strange outlier that somehow cheated the rules of cosmic evolution? Or was it a signpost, evidence that the story of the universe's beginning is far more complex and far more mysterious than we ever dared to believe? Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. The James Webb Space Telescope had just begun its mission. Yet with this first revelation, it cracked open a mystery so deep that it threatened to rewrite astronomy from the ground up. For more than a century, scientists have built an extraordinary story about how the universe grows. It begins with the Big Bang, a fiery birth when space and time themselves exploded into being. Out of that chaos, hydrogen and helium filled the cosmos, and over countless eons, gravity slowly pulled matter together into stars and galaxies. This is the foundation of what's known as the standard model of cosmology. According to this model, the universe unfolds in clear stages. First, the Dark Ages, then the ignition of the first stars, followed by small, irregular galaxies, and finally, billions of years later, the elegant spiral and elliptical galaxies we see today. Everything has its place on the timeline. Nothing skips ahead. At least, that's what we thought. When the James Webb Space Telescope revealed that ancient spiral galaxy, the discovery wasn't just surprising. It was a direct contradiction of the timeline written into the standard model. By all accounts, such a galaxy shouldn't have existed until at least a few billion years after the Big Bang. The physics we relied on told us that galaxies needed vast amounts of time to gather matter, to recycle stars, and to sculpt themselves into complex forms. Yet here was proof that nature had found a way to fast-forward the process. It was as if the universe had pressed the skip button on its own evolution. Instead of a baby galaxy struggling to form, Webb had uncovered one that looked like it had already lived through an entire cosmic childhood and adolescence. In less than 500 million years, it had achieved what should have taken more than 10 billion. This discovery shook the very ground of cosmology. If galaxies could mature that quickly, what else about our model might be wrong? Were we miscalculating the age of the universe? Were our measurements of distance and redshift missing something critical? Or had we misunderstood the very forces that shape the cosmos? Gravity, dark matter, and the expansion of space itself. The unsettling truth is that science thrives on consistency. When evidence aligns with theory, confidence grows. But when evidence defies the theory, as this galaxy did, it forces us back to the drawing board. Suddenly, every textbook explanation of cosmic history seemed fragile, incomplete, perhaps even outdated. Astronomers who had spent decades refining the standard model now faced a haunting question. What if the timeline we built for the universe is fundamentally flawed? If galaxies could leap ahead billions of years in their development, then our entire chronology of cosmic evolution may be off by a staggering margin. And this wasn't a quiet, hidden debate. The Webb discovery echoed through universities, observatories, and research institutes around the globe. Some scientists clung to the hope that the data might be misinterpreted, that maybe the galaxy wasn't as old or as distant as it appeared. Others embraced the chaos, arguing that these findings signaled the dawn of a new era in physics, one where bold theories would be needed to explain the impossible. In the end, the standard model of cosmology, the trusted roadmap of the universe, had been violated. The discovery of this ancient spiral galaxy was more than a surprise. It was a warning sign that the universe still holds secrets powerful enough to upend everything we thought we knew about time, space, and cosmic history. When scientists study distant galaxies, they don't just look at their shapes or their brightness. They read their light. Using spectroscopy, the James Webb Space Telescope breaks starlight into a cosmic fingerprint, revealing the hidden chemistry of stars, gas, and dust across unimaginable distances. What Webb uncovered inside this early galaxy wasn't just strange, it was revolutionary. According to the standard model of cosmology, the very first stars, known as population 3 stars, were made almost entirely of hydrogen and helium, the two simplest elements created in the Big Bang. These stars were expected to burn hot, live short lives, and die in dramatic explosions, but their chemistry would have been primitive and pure. If this galaxy had formed so soon after the Big Bang, scientists expected to see the same signature, the raw ingredients of a universe only just beginning. But Webb's instruments revealed something altogether different. The galaxy wasn't made of only hydrogen and helium. Its spectrum was marked by the fingerprints of carbon, oxygen, iron, magnesium, and even platinum, heavy elements that were never supposed to exist at such an early stage of cosmic history. This was a staggering revelation. These metals, as astronomers call them, can only be forged in the hearts of stars. They're created through nuclear fusion, released in supernova explosions, and scattered into space, where they seed the birth of new stars and planets. In other words, the presence of these elements means that the galaxy had already gone through multiple life cycles. Stars had been born, lived out their lives, exploded, and enriched the surrounding gas, over and over again, all within just a few 100 million years. That's not just fast, it's impossibly fast. The implication was clear. The early universe wasn't a quiet nursery of slowly forming stars. It was a furnace, an engine running at full speed, producing complex chemistry at a pace that defied every expectation. This changes the entire narrative of cosmic history, because without heavy elements, planets like Earth could never form. Without carbon or oxygen, life as we know it could never exist. And yet, here we find a galaxy so early, so impossibly young, already brimming with the raw ingredients of life. Think about that for a moment. The universe, in less than 500 million years, had already created the elements that billions of years later would form you, me, and everything we know. For astronomers, the questions multiplied. How could so many massive stars form, live, and die in such a short cosmic span? Was star formation in the early universe far more aggressive and efficient than we ever imagined? Or was there some other unknown process at work, something beyond the limits of current physics, accelerating the creation of heavy elements? The deeper scientists looked, the more impossible it seemed. Instead of a quiet, simple beginning, the cosmos appeared to have raced ahead, producing complex chemistry almost as soon as it was born. And if heavy elements were present that early, it raised a profound possibility. Perhaps the building blocks of planets and even life could have emerged not billions of years later, but almost immediately after the dawn of time itself. The James Webb Space Telescope wasn't just rewriting textbooks. It was rewriting the origin story of the universe. Galaxies are not all the same. Some are ragged and shapeless clouds of stars, others are smooth, glowing ellipses, and a few, like our own Milky Way, are breathtaking spirals, with arms unfurling across the cosmos like the strokes of a cosmic painter's brush. But spirals don't just appear out of nowhere. They are the result of time, gravity, and stability. To form a stable disk with spiraling arms requires billions of years of cosmic choreography. Stars must orbit in balance, dark matter halos must hold the structure together, and gravitational interactions with neighboring galaxies often help shape the delicate arms we see. That's why, when the James Webb Space Telescope locked its golden mirrors on this ancient galaxy, astronomers were stunned. What they expected to see was a young, chaotic system, irregular, clumpy, turbulent, a galaxy still in its infancy. Instead, Webb revealed something no one was prepared for: a fully realized spiral, complete with elegant arms, a bright and stable core, and even hints of a barred structure cutting through its center. This wasn't just surprising, it was impossible, at least according to our current understanding. Spiral arms require order and time, not chaos and youth. A barred spiral requires an even deeper level of stability, something thought to emerge only in galaxies billions of years old. Yet here it was, glowing softly in the distant past, only a few 100 million years after the birth of the universe. The implications were profound. This galaxy wasn't supposed to exist, not in this form, not in this era. For it to have such structure, it must have experienced long-term gravitational interactions, the kind of cosmic conversations between stars, dark matter, and surrounding galaxies that we believed took eons to unfold. But if such complexity already existed, then our entire timeline of galactic evolution was wrong. Astronomers stared at the Webb images and asked the unthinkable: how could such an organized, mature galaxy exist when the universe itself was barely out of its infancy? Was the cosmic clock somehow running faster than we thought? Or was there an entirely new set of rules guiding galaxy formation in the early universe? Rules we have yet to uncover. For decades, cosmologists taught that galaxies slowly transformed from chaotic lumps into majestic spirals. But Webb's discovery showed that perhaps spirals were not a late development at all. Maybe they were there from the very beginning, carved into the fabric of the cosmos far earlier than anyone dreamed possible. This galaxy wasn't just a structure, it was a message, a reminder that the universe is capable of refinement and beauty even in its earliest hours, a signal that the laws we thought we understood may not tell the full story. Because if a barred spiral galaxy can exist within a few 100 million years of the Big Bang, then what else is out there, hidden in the deep dark, waiting to shatter our understanding of cosmic history? The James Webb Space Telescope had pulled back the curtain, and what it revealed was nothing short of revolutionary. The early universe was not primitive and unrefined. It was already painting masterpieces. When astronomers first measured the IB, light coming from this ancient galaxy, something unusual stood out. The glow wasn't steady. It flickered ever so slightly, showing fluctuations in brightness that didn't match the calm shine of ordinary stars. Instead, it resembled something far more powerful and far more puzzling. The signature looked strikingly similar to that of a quasar. Quasars are among the brightest objects in the universe, capable of outshining entire galaxies. But they are not stars. They are the blazing hearts of galaxies where supermassive black holes devour matter at incredible speeds. Picture this: a black hole millions, even billions, of times the mass of our sun, pulling in gas, dust, and stars. As this material spirals inward, it forms an accretion disk, a whirling ring of matter heated to such extreme temperatures that it shines across the universe. That violent, radiant energy is what we call a quasar. But here's the paradox. To build a black hole that massive takes time, a lot of time. Even the most optimistic models suggest hundreds of millions, if not billions, of years for black holes to grow from small seeds into the giants we see in the modern universe. And yet, in this galaxy, only a few 100 million years after the Big Bang, we already see signs of one. This wasn't supposed to be possible. According to standard cosmology, the first stars, huge and unstable, may have collapsed into black holes within a few million years. These seed black holes might have been dozens or even hundreds of times the mass of our sun. But from there, growth is painfully slow. To reach millions or billions of solar masses requires an immense amount of matter and vast stretches of cosmic time. And yet Webb's observations tell a different story. Somehow, in what amounts to the blink of an eye on the cosmic clock, black holes had not only formed, they had matured. They were already anchoring galaxies, shaping their surroundings, and blazing as quasars, visible across billions of light years. The problem is not just their size, but their speed. If these supermassive black holes truly existed so early, it means either our theories of black hole growth are wrong, or there is a missing mechanism, something unknown, that allowed black holes to skip the line, growing at rates far beyond what physics currently allows. Some scientists suggest that instead of small seed black holes, perhaps the early universe created direct collapse black holes, giants born instantly with hundreds of thousands of solar masses. Others speculate about exotic physics, where conditions in the infant cosmos made growth vastly more efficient than it is today. Whatever. The explanation, the implications are staggering. Black holes, once thought to be the slow-growing monsters of the universe, may instead have been present from the very beginning, shaping the evolution of galaxies from the dawn of time. And if quasars already existed when the universe was less than 500 million years old, then the story of cosmic evolution is not one of gradual buildup, but of explosive, immediate complexity. The James Webb Space Telescope had done more than detect a galaxy. It had uncovered a paradox: black holes too big, too early, existing in defiance of everything we thought we knew. It was as if the universe itself was whispering a secret. You still don't understand how I began. The James Webb Space Telescope was supposed to confirm our theories, to fill in the gaps, to give us sharper images of a story we already thought we understood. Instead, it cracked open a box of questions so profound that some scientists began to wonder if the very laws of physics themselves might need rewriting. The discoveries, spiral galaxies impossibly early, heavy elements where none should exist, and supermassive black holes born before their time, did not fit into the neat framework of the standard model of cosmology. That model is built on pillars: dark matter, dark energy, general relativity, and the Big Bang timeline. Webb's findings were shaking those pillars one by one. Faced with evidence that didn't add up, scientists began exploring possibilities once thought too radical to discuss outside of science fiction. One possibility: dark matter, the invisible scaffolding that shapes galaxies, may not behave the way we think. In our models, dark matter is cold, slow-moving, and passive. But what if, in the early universe, dark matter was more dynamic, interacting in ways we've never considered? Could its hidden influence have accelerated the growth of galaxies and black holes, creating order far sooner than expected? Another possibility: perhaps we're misinterpreting the very thing we use to measure distance and time, the redshift of light. For decades, astronomers have trusted that the stretching of light tells us how far away and how old distant galaxies are. But what if that interpretation is flawed? What if these galaxies aren't as ancient as we believe, but instead much closer, masquerading as relics of the dawn of time? Others have suggested that the problem may lie not in the data, but in the laws of gravity themselves. Einstein's theory of relativity has passed every test within our solar system. But what if, on the grandest scales of the universe, gravity behaves differently? Could a modified law of gravity explain the rapid, early organization of galaxies and the explosive growth of black holes? And then there are the truly bold ideas. Some theorists whisper about the possibility of parallel universes or higher dimensions, realms beyond our perception that may have influenced our own in those chaotic first moments after the Big Bang. Could the strange order we're seeing be the fingerprints of another universe bleeding into ours, leaving traces in the form of galaxies that should not yet exist? Each of these ideas challenges not just a theory, but the foundation of modern science itself. To accept them would mean admitting that our understanding of space, time, and reality is incomplete, perhaps even deeply flawed. What Webb has shown us is that the universe is not obliged to follow our expectations. It is more complex, more mysterious, and more alive with possibilities than we ever dared to imagine. And so, with every image and every spectrum it sends back, the telescope is not just expanding our view of the cosmos, it is forcing us to confront the limits of human knowledge. The early universe was supposed to be simple. Instead, it was already bursting with galaxies, black holes, and heavy elements, as though the laws of physics were playing by a different set of rules. The question now is not just how the universe began. The question is, are we even asking the right questions? When the James Webb Space Telescope sent back images of galaxies that should not exist, the scientific community found itself standing at the edge of reason. The data was clear, but the explanations? They grew stranger with every passing month. For some scientists, the only way to reconcile the impossible was to think the unthinkable. One radical proposal was the idea of cosmic time bubbles. Imagine a universe where time itself does not flow evenly. In some regions, it runs faster. In others, slower. If the galaxies Webb detected happened to form inside one of these bubbles, then they would have experienced accelerated evolution. To us, they appear impossibly advanced, but within their own frame of reality, they had far more time to grow. This idea challenges the very notion of a universal cosmic clock, suggesting that time is not uniform, but patchy, fragmented, and fluid. Other theorists push the speculation even further. What if what Webb is really showing us are not new galaxies at all, but echoes of a previous universe? According to the theory of cosmic cycles, the Big Bang was not the beginning, but merely the latest rebirth in an eternal sequence of expansion and collapse. The galaxies we see might be fossils, structures that survived from a universe before ours, carried over in ways we cannot yet comprehend. If true, Webb may have accidentally glimpsed not just the beginning of our cosmos, but the memory of a universe long dead. And then there are the most mind-bending ideas of all. Some physicists inspired by quantum theory and information science, have suggested that reality itself might not be what it seems. According to the holographic principle, our universe could be a kind of projection, a three-dimensional illusion cast from information encoded on a distant cosmic surface. If that's the case, then what Webb revealed might not be galaxies breaking the rules, but glitches, anomalies in the projection of reality itself. Like a skipped frame in a film reel or a corrupted pixel in a digital image, these galaxies could be evidence that the fabric of the universe is not continuous, but structured, coded, and fallible. Of course, these ideas sound fantastical. Cosmic time bubbles, recycled universes, holographic glitches. These are not the kind of explanations you'll find in standard astronomy textbooks. And yet, the universe is forcing us to consider them. The data is too compelling to ignore. Webb was built to peer deeper than ever before. But no one expected that depth to lead us here, to the very edges of science, where the line between physics and philosophy blurs. What is time? What is reality? What is the true nature of the universe we inhabit? The telescope hasn't answered those questions. Instead, it has raised them with greater urgency than ever before, daring us to think beyond the safe boundaries of known science. Perhaps the greatest discovery of all is not the galaxies themselves, but the realization that the universe is far stranger, far more mysterious than even our boldest imaginations had prepared us for. At first, some skeptics tried to dismiss Webb's discovery as a miscalculation. Perhaps it was a calibration error in the instruments, or a cosmic mirage created by the bending of light. After all, astronomy is delicate work. Tiny misinterpretations can lead to dramatic conclusions. But then Webb kept looking, and what it found shattered the hope that this was merely a mistake. It wasn't just one galaxy defying the rules of cosmic evolution. It was dozens. Each time Webb turned its golden mirrors toward the deep past, the same story repeated itself. Galaxies that were impossibly massive, impossibly refined, and impossibly ancient. Some of these galaxies were as large as our own Milky Way, yet they existed only a few 100 million years after the supposed birth of the universe. According to everything we thought we knew, galaxies of this scale should have taken billions of years to assemble. Their structures should have been chaotic, irregular clumps, not elegant spirals with defined arms and luminous cores. But the wordy anomalies didn't stop at size and structure. The chemical signatures told the same impossible tale. These early galaxies weren't made of pristine hydrogen and helium alone. They were enriched with carbon, oxygen, iron, even rare heavy elements, like platinum. This meant that entire generations of stars had already lived, exploded, and seeded the cosmos with metals long before such a process was thought possible. And, perhaps most unsettling of all, some of these galaxies showed hints of active black holes, even quasars, blazing at their centers. These would require supermassive black holes, millions, even billions of times the mass of our Sun, already fully formed at the dawn of cosmic time. At this point, coincidence was no longer an option. One outlier might be an error, two might still be a fluke. But a growing catalog of such galaxies, all telling the same forbidden story? That was a revelation. It became clear that the universe was hiding an entire chapter of its history from us. A chapter that our textbooks had skipped, that our equations had overlooked, that our theories could not yet explain. The implications were staggering. If galaxies were forming faster, growing larger, and evolving sooner than we believed, then our timeline of the cosmos was deeply flawed. The Big Bang may not have been the clean, simple beginning we imagined. The early universe was not a quiet, dark expanse slowly coming to life. It was already vibrant, structured, and burning with complexity. For scientists, this was both thrilling and terrifying. It meant that everything we thought we knew about the origins of galaxies, stars, and black holes had to be reconsidered. Webb was not just rewriting a detail or correcting a small error. It was uncovering a hidden truth about the very fabric of cosmic history. And as image after image streamed back to Earth, one thing became undeniable. The anomalies were not anomalies at all. They were the universe revealing its true story. A story far stranger and far older than we ever dared to imagine. The James Webb Space Telescope was designed to explore galaxies, stars, and cosmic history. But its discoveries may have implications far closer to home, or at least far closer to the question of life itself. When Webb revealed that galaxies in the early universe were already chemically rich, it wasn't just a triumph of cosmology. It was a hint that the ingredients for planets, oceans, and perhaps even life were available far earlier than anyone imagined. We once thought that the universe had to age for billions of years before forming rocky planets. Heavy elements like carbon, oxygen, iron, and magnesium are essential for planet building. Without them, there's no crust, no oceans, no atmosphere capable of supporting chemistry like we see on Earth. But these early galaxies contained those elements in abundance. This implies that stars had already lived, exploded, and seeded the cosmos with metals, making planet formation possible hundreds of millions of years after the Big Bang, not billions. The universe may have been ready for Earth-like worlds long before our solar system even existed. And it's not just the possibility of planets, it's the possibility of life. Where there are rocky planets with water and organic compounds, the basic building blocks of life may also be present. If the universe became hospitable so early, could life itself have emerged far earlier than we ever imagined? Could civilizations have arisen and fallen eons before humans even walked the Earth? This isn't just speculation. Webb's spectral data shows the signatures of molecules like carbon monoxide, carbon dioxide, and even hints of complex organics in young galaxies. These are the chemical seeds from which life could sprout. The timeline for cosmic biology may need to be rewritten, opening the door to civilizations older than our entire planet. The implications are staggering. If life could arise in these early galaxies, the universe may be teeming with ancient, advanced worlds whose histories are unknowable to us. Planets, oceans, and perhaps civilizations could have existed long before the sun ignited, invisible in the darkness until now. Webb's findings force us to ask profound questions. Are we alone? Or are we part of a cosmic story that began billions of years before Earth? How many worlds could have formed, evolved, and perhaps even fallen into ruin, leaving behind no trace but the chemical fingerprints in ancient galaxies? For the first time, it feels as if the universe itself is inviting humanity to expand its imagination, not just to ponder the origins of stars and galaxies, but to imagine the possibility of life on a scale and age that dwarfs our own existence. Webb isn't just showing us the cosmos, it's showing us what life might have looked like in the earliest chapters of the universe. And in doing so, it transforms our understanding of what is possible and how deeply interconnected we are with the vast expanse of space and time. The discoveries of the James Webb Space Telescope did more than rewrite textbooks. They shook the very foundation of science. What began as a mission to study the first galaxies quickly evolved into a journey that challenged humanity's understanding of reality itself. Astrophysicists, quantum physicists, and even philosophers of science were forced to confront a sobering truth. Our models of the universe are incomplete. The elegant equations and simulations that have guided cosmology for decades suddenly seemed like approximations, hints, rather than definitive answers. The universe revealed itself as far stranger, more complex, and less predictable than we had imagined. The revelations were humbling. Galaxies forming faster than physics allowed. Heavy elements appearing almost immediately after the Big Bang. Supermassive black holes and quasars lighting up a cosmic dawn we thought was still dark. These were not isolated anomalies. They were evidence that the universe contains structures, laws, and histories beyond human imagination. And yet, this uncertainty was not discouraging. It was exhilarating. Webb didn't just provide data. It ignited a revolution. Scientists no longer sought merely to confirm theories. They were compelled to ask deeper, more profound questions. Questions that bridged disciplines. Could our understanding of time itself be incomplete? Could life exist on planets formed billions of years before Earth? Could reality itself hold layers we have not yet glimpsed? This is the beginning of a new era, a renaissance of curiosity, one where mystery is not a failure of knowledge, but the fuel for discovery. Every image Webb sends back, every spectral signature it records, is a reminder that the cosmos is alive with secrets, daring us to explore further. The telescope has opened a door to possibilities that stretch beyond the limits of imagination. It challenges us to think bigger, to question harder, and to accept that some answers may be beyond our current reach. In doing so, it reminds us that science is not a static body of knowledge. It is a dynamic journey, ever-changing, ever-expanding, propelled by wonder, skepticism, and awe. The universe is no longer just an object of study. It is a frontier of the mind, a canvas of mysteries waiting to be painted with insight. And at the heart of this frontier is the James Webb Space Telescope, a beacon illuminating the unknown, daring humanity to chase the questions that may never have simple answers. We are witnessing not just the observation of galaxies, but the birth of a scientific revolution. A revolution where uncertainty is celebrated, curiosity reigns, and the universe, in all its vastness and strangeness, invites us to explore its deepest secrets. The cosmos has spoken, and humanity is listening, more boldly, more imaginatively, and more determinedly than ever before. As the James Webb Space Telescope continues to send its golden mirror glimpses across the universe, one truth becomes unmistakably clear. We are only beginning to understand the cosmos. Each discovery, each anomaly, each galaxy out of place is a reminder that the universe is far stranger and more wondrous than we ever imagined. We have glimpsed galaxies that defy time, elements that hint at early life-building chemistry, and black holes that challenge the very rules of physics. We have stared into the cosmic past and realized that reality itself may be more complex, more layered, and more mysterious than textbooks can explain. And yet, this is not a story of despair. It is a story of possibility. Possibility that worlds older than Earth could host life, that mysteries await in the farthest reaches of space, and that humanity's curiosity is the spark that allows us to chase these cosmic secrets. The universe is no longer a distant backdrop. It is a living, unfolding story, and we are part of it. What we once thought impossible is now within reach of our imagination, guided by the extraordinary eye of the James Webb Space Telescope. So, the question is no longer whether we can understand the universe, but how far are we willing to go to explore it? The answers lie ahead, in the light of galaxies we have yet to discover, in the secrets we have yet to unravel, and in the mysteries that will continue to challenge and inspire every generation of explorers, dreamers, and thinkers. The cosmos awaits, and the adventure has only just begun. If you found this journey through time and space as mind-blowing as we did, subscribe now to follow the latest cosmic discoveries. Share your thoughts in the comments. What do you think these ancient galaxies mean for life, the universe, and our place within it? Let's explore the unknown together. "6 minutes. That's all the time astronomers had to coordinate a global emergency response when Atlas appeared in our telescopes, behaving like nothing we'd ever seen before. Picture this: ground control rooms erupting into organized chaos, ESA servers calculating trajectories at breakneck speed, and the most expensive space telescope ever built pivoting away from years of scheduled observations to focus on a single, terrifying anomaly. What they discovered in those crucial minutes of observation has left the scientific community scrambling for explanation, and what we're about to reveal will show you exactly why this discovery is being called worse than anyone expected. On August 6, 2025, the James Webb Space Telescope entered a rare and critical emergency override to capture data on 3I Atlas, an interstellar object unlike anything astronomers had observed before. Normally, JWST operates on a strict schedule, with every observation carefully planned weeks or even months in advance, balancing the delicate choreography of orbital mechanics, fuel consumption, and instrument availability. Pausing this finely tuned program is not done lightly, as even a small miscalculation can cost days or weeks of science, or risk damaging sensitive subsystems. The urgency arose from ground-based observations showing that 3I Atlas was accelerating and displaying unexpected spectral signatures. Within minutes, the mission operations team had to decide whether to override the main science program. Approval for such an override required unanimous agreement from the highest levels of the project, including the project scientist, because the risks were high and the opportunity fleeting. The telescope pivoted, instruments activated, and the entire operations center was on high alert, monitoring every telemetry signal as the team raced to ensure nothing went wrong. This emergency intervention was historic because JWST had only performed a handful of overrides since its launch, and none had ever targeted an interstellar object. Every other observation, from distant galaxies to exoplanet atmospheres, was temporarily suspended. The situation underscored the extraordinary nature of 3I Atlas, which was behaving in ways that broke the normal rules for comets, prompting astronomers to mobilize their resources instantly to capture a fleeting window of unprecedented data. The override not only demonstrated the telescope's flexibility but also highlighted the stakes involved in studying interstellar visitors. Unlike typical comets, whose paths and chemical compositions are relatively predictable, 3I Atlas demanded immediate, full-scale attention. Its arrival was a rare cosmic event, and missing it could mean losing the chance to understand a body formed in conditions potentially very different from anything in our solar system. The tension in the control room was palpable as scientists worked against the clock, knowing that any delay or error could compromise the mission, but also that the data they were about to capture could reshape everything we know about interstellar objects. This moment marked the beginning of a high-stakes observation campaign that would uncover chemical, physical, and dynamic properties of 3I Atlas that had never before been recorded, setting the stage for a story of cosmic anomalies, scientific debate, and mysteries that reach back into the very history of human observation of the heavens. Astronomers had anticipated that 3I Atlas would behave like a typical icy comet, slowly releasing water vapor and forming a faint, predictable tail as it approached the sun. Instead, the first data packets from JWST painted a picture that defied every expectation. The comet's coma was saturated with carbon dioxide at levels never recorded before, and the instruments detected metallic nickel in abundance while iron, normally found alongside nickel in comets and meteorites, was almost completely absent. This chemical imbalance was so extreme that seasoned experts in interstellar bodies described the numbers as alarming, even terrifying. The comet was already active far from the Sun, at a distance beyond Jupiter where sunlight is weak and most comets remain dormant. Instead of the usual sublimation of water ice that drives comet activity, 3I Atlas was venting sheets of carbon dioxide gas, a process that normally requires much more heat. The tail, thin and ghostly due to the scarcity of dust, extended for hundreds of thousands of kilometers, growing far faster than standard models would predict. Observations from other telescopes, including Gemini South and Hubble, confirmed these unexpected phenomena, ruling out calibration errors or instrumental glitches. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. Every team cross-checked the data against known comet behaviors and previous interstellar visitors. Even Borisov, the last interstellar object to pass through the solar system, did not approach these levels of carbon dioxide dominance or the extreme nickel-to-iron ratio. The production rates calculated from the spectra showed carbon dioxide pouring out at 8 times the rate of water, a ratio completely off the charts. Dust, normally a major contributor to the brightness and structure of a comet's tail, was nearly absent, making the comet appear almost ethereal, as though it were glowing from the gas itself. Scientists immediately realized that this object was not just unusual, it was a chemical enigma. The composition suggested a parent body formed under conditions vastly different from those in our solar system, perhaps in an environment where water was scarce and carbon dioxide ices dominated. Alternatively, it might reflect an unknown chemical or physical process that had never been observed. Whatever the explanation, 3I Atlas was rewriting the rulebook for how comets form and behave, challenging decades of expectations and sparking intense excitement and concern among astronomers around the world. The implications of these initial observations went beyond mere curiosity. The chemical signatures hinted at a history and origin completely alien to the solar system, raising fundamental questions about interstellar chemistry and the diversity of planetary systems. Scientists were suddenly looking at a visitor whose very makeup seemed to defy the laws and patterns established by centuries of comet studies, signaling that the story of 3I Atlas was only beginning to unfold. Ground-based telescopes immediately began sending real-time observations of 3I Atlas as soon as its unusual behavior was noticed. Every new measurement mattered, as the comet was accelerating unpredictably and its trajectory was shifting by the hour. Teams across multiple observatories scrambled to track its path, gathering positional data that could determine exactly where JWST needed to point. This was not a routine calculation. The object's erratic movements meant even minor delays could result in missing the observation window entirely. ESA servers took the incoming data and ran rapid, complex calculations to produce precise coordinates for JWST. The process required accounting for the telescope's orbital mechanics, fuel constraints, and instrument alignment, ensuring that NIR spec and other sensitive instruments could lock onto the object immediately. Any error, even by a fraction of a degree, risked losing the opportunity to collect critical spectral data or wasting precious observation time. In less than 6 minutes from the initial alert, the emergency override command sequence was transmitted to JWST. The telescope pivoted in real time, its sensors activating as engineers monitored the telemetry for any sign of malfunction. Every eye in the operations room was fixed on the incoming data stream, waiting for the first packets to confirm that the comet was within range and that the instruments were functioning as intended. This coordination showcased the remarkable precision and flexibility of modern space observatories. What normally takes weeks of planning and committee approval was executed in mere minutes, driven by urgency and the extraordinary nature of 3I Atlas. The teams had to ensure not only that JWST captured the object, but that it did so without compromising the telescope's long-term mission or risking any critical subsystem. The success of this rapid response was a testament to years of preparation, cross-agency collaboration, and the ability to pivot quickly when the cosmos presents something truly unprecedented. In those tense minutes, the observatories on Earth and the telescope in space became a single, synchronized system, ready to capture data that would challenge every expectation of what an interstellar visitor could be. The chemical composition of 3I Atlas immediately stunned astronomers. Unlike typical comets, where water ice dominates activity and drives the formation of tails as the object approaches the Sun, this interstellar visitor was already highly active at 6 astronomical units, well beyond Jupiter's orbit, where sunlight is weak and most comets remain dormant. Instead of water, carbon dioxide was the primary volatile being released, venting at rates 8 times higher than water. This ratio of 8 to 1 is extraordinary, as even the most unusual solar system comets rarely exceed a ratio of 0.7. The tail of 3I Atlas reflected this unusual chemistry. With very little dust present, the tail appeared thin and ghostly, illuminated mainly by gas rather than solid particle. The carbon dioxide was not only abundant, but actively shaping the coma and tail in ways that defied expectation. Observations from multiple instruments, including JWST's NIR SPEC and other ground-based telescopes, confirmed that the activity was consistent and not an observational artifact. The gas sheets and faint brightening were persistent, indicating a steady outflow rather than a transient flare. This early activity so far from the Sun suggested that the comet's composition and thermal properties were fundamentally different from known comets. In a typical solar system comet, water ice begins to sublimate at closer distances, while CO2 and other volatiles contribute only later and to a lesser extent. In contrast, 3I Atlas seemed to have a main engine fueled by carbon dioxide, operating efficiently in the deep freeze of the outer solar system. The implications were profound. The composition hinted that 3I Atlas might have formed in an environment unlike anything in our solar system, possibly in a region where water was scarce and carbon dioxide ices dominated. Alternatively, it could indicate a process previously unknown to science, one capable of producing a volatile-rich body that activates so far from a star. The comet's early activity and extreme chemical ratios challenged existing models, forcing astronomers to reconsider assumptions about how interstellar objects form, evolve, and behave as they enter new star systems. As the data continued to stream in, it became clear that 3I Atlas was not just unusual, it was a chemical anomaly that could rewrite the rules for what comets can be, marking the beginning of an entirely new chapter in the study of interstellar visitors. Spectroscopic analysis of 3I Atlas revealed a chemical signature unlike anything seen before. The instruments detected strong and consistent nickel spectral lines spanning the ultraviolet and near-infrared bands, indicating a significant presence of metallic nickel in the comet's composition. At the same time, iron lines, which are normally found alongside nickel in both solar system comets and meteorites, were completely absent. The result was a nickel-to-iron ratio exceeding 40 to 1, a disparity so extreme that it defied all previous observations of celestial bodies. This anomaly was striking because, in typical comets and interstellar objects, nickel and iron appear together in roughly cosmic proportions. Even Borisov, the last well-studied interstellar visitor, adhered to these ratios, maintaining the expected balance between nickel and iron. With 3I Atlas, however, the absence of iron suggested either a formation process unlike anything known or conditions that selectively favored nickel over iron. Scientists considered every possibility, from instrumental errors to contamination, but repeated cross-checks with multiple telescopes and instruments confirmed that the signal was genuine. The presence of nickel in isolation hinted at extreme or exotic conditions in the comet's formation environment. Laboratory experiments suggest that volatile compounds like nickel carbonyl can form under certain conditions, but for iron to remain nearly absent, the parent body would likely need to have originated in a region where iron was trapped in minerals or otherwise unable to form volatile compounds. No known solar system comet shows this pattern, making 3I Atlas chemically unique and forcing astronomers to confront possibilities outside standard models of comet formation. This chemical anomaly also raised broader questions about the diversity of planetary systems. If an object could form with such a skewed composition, it implied that other star systems might produce worlds with chemistry radically different from our own. The data challenged assumptions about interstellar chemistry and hinted at processes in distant nebulae or planetary formation regions that humanity has never observed. The nickel dominance and iron absence did more than shock scientists. They suggested that 3I Atlas might carry information about a completely alien environment, offering a rare window into cosmic conditions that are otherwise inaccessible. Every measurement reinforced the idea that this comet was extraordinary, unlike anything seen before, and its chemical fingerprint was just the beginning of a puzzle that would unfold over the coming observation. Observations of 3I Atlas revealed that its motion was as unusual as its chemistry. Tracking networks, including pan-stars, recorded acceleration deviations that defied all expectations based on gravity and standard outgassing behavior. Over a span of just 72 hours, the comet's velocity increased by roughly 0.12 meters per second squared, an amount far greater than could be explained by solar heating or jets of gas alone. For an object approximately 11 kilometers across, this was comparable to witnessing a massive ship gain speed in the ocean without engines or wind. Even more perplexing were the tiny, abrupt jitters layered on top of the main acceleration. The comet's trajectory did not follow a smooth curve dictated by gravitational forces, but instead displayed subtle, sharp deviations as if something inside or attached to the object was intermittently pushing it forward. Analysts meticulously checked for software errors, instrument malfunctions, and observational biases, but all raw astrometry held firm. The acceleration was real, persistent, and completely anomalous. Photometric observations added another layer of mystery. Data from Gemini South and TESS revealed a periodic brightening every 7.2 hours, resembling a lighthouse beam sweeping across the sky. This rhythmic modulation was too regular to be explained by the slow tumble of a natural comet, and models attempting to account for it through irregular shape or rotation failed to reproduce the precision of the signal. Some researchers speculated about hollow or sheet-like structures reflecting sunlight, but each hypothesis presented its own problems. The combination of acceleration anomalies and precise light curves drew immediate comparisons to Oumuamua, another interstellar object whose trajectory and behavior defied conventional physics. However, 3I Atlas was larger, brighter, and exhibited a sharper, almost mechanical rhythm in its brightness changes. The more astronomers studied it, the more the object appeared to challenge both natural and previously understood cosmic processes. These dynamic irregularities elevated 3I Atlas from a chemical curiosity to a physical enigma. The data suggested that forces or mechanisms beyond standard cometary physics were at play, forcing scientists to consider exotic natural processes or, cautiously, the possibility of artificial or engineered structures. Every new observation intensified the debate, as the object's movement and light signature refused to conform to any familiar model. Photometric observations of 3I Atlas revealed a pattern that confounded astronomers. Data collected from Gemini South and TESS showed a precise, repeating brightening every 7.2 hours, a rhythm so regular it resembled the sweeping beam of a lighthouse. Unlike ordinary comets, which exhibit irregular rotations and unpredictable variations in brightness due to uneven surfaces and chaotic tumbling, 3I Atlas maintained an almost clockwork consistency in its light curve. Scientists attempted to model the phenomenon using natural explanations. They considered the possibility of a tumbling, irregularly shaped comet or a hollow, sheet-like structure reflecting sunlight at certain angles. Yet every model failed to reproduce the sharpness and regularity of the observed brightness changes. The period did not slow as the comet outgassed, contradicting expectations from rotational physics, and no combination of known shapes and reflective properties could account for the observed modulation. The precision of the light curve, combined with the unusual chemical composition and acceleration anomalies, pushed researchers to contemplate possibilities beyond conventional cometary physics. Some began to speculate about artificial or engineered structures, noting that a thin, reflective object could produce both the consistent periodic brightening and the anomalous accelerations observed. While no one claimed proof of design, the data forced scientists to confront scenarios that were once considered purely science fiction. The mechanical-like behavior heightened the sense of mystery surrounding 3I Atlas. Every observation contradicted prior, assumptions about how interstellar objects should behave, and the unusual combination of chemistry, motion, and brightness forced astronomers to consider that they were observing something entirely new. It was no longer merely a comet. It was a cosmic enigma challenging the boundaries between natural phenomena and possible engineered origins. The 7.2-hour light curve became a central focus of study, with astronomers worldwide analyzing the data, debating models, and checking for any possible observational error. Yet every cross-check confirmed the regularity. The object seemed to follow a rhythm unlike anything else in the solar system, or even among previously discovered interstellar visitors. This pattern, combined with all the other anomalies, marked 3I Atlas as one of the most extraordinary celestial objects ever observed. Throughout history, humans have encountered rare metals from the sky, long before advanced metallurgy existed. Archaeologists have discovered nickel-rich artifacts in ancient civilizations that far exceed what could have been produced by earthly smelting techniques. Tiny Egyptian beads, hammered and rolled into delicate shapes more than 5,000 years ago, contain nearly 1/3 nickel, a ratio that natural furnaces of the era could not achieve. Similarly, ceremonial daggers buried with pharaohs, such as those found with Tutankhamun, exhibit high nickel content along with traces of cobalt, consistent with meteorite composition rather than terrestrial iron. These artifacts reveal that cosmic material has been reaching Earth for millennia, sometimes incorporated into objects of cultural and ceremonial significance. The unique nickel-to-iron ratios in these items match patterns found in meteorites and echo the anomalies now seen in 3I Atlas. Scholars studying these relics note the crystalline structures, including the Widmanstätten pattern, which form only in the slow cooling of metallic cores in space, confirming a non-terrestrial origin. The connection between these ancient skyfall metals and the composition of 3I Atlas is striking. Just as ancient humans recognized these metals as extraordinary, often imbuing them with mystical or religious significance, modern astronomers now encounter a celestial object that carries a similarly unusual chemical signature. The recurrence of nickel-rich material, both in historical artifacts and in this interstellar visitor, suggests a cosmic consistency, a material fingerprint delivered across space and time. This historical context provides not only a fascinating link between past and present, but also underscores the universality of nickel in certain celestial processes. It raises profound questions about how often such material reaches planetary systems, the environments that produce it, and the potential insights it holds into the formation of bodies beyond our solar system. In 3I Atlas, scientists are observing in real time the same kind of cosmic fingerprint that humans have been discovering on Earth for thousands of years, bridging ancient wonder with cutting-edge astrophysical discovery. The unprecedented combination of chemical, dynamic, and photometric anomalies in 3I Atlas has ignited intense debate within the scientific community. On one side, some researchers argue for rare but natural explanations, suggesting that the comet's unusual nickel-to-iron ratio, extreme carbon dioxide dominance, and early activation could result from formation in a carbon-rich nebula or a parent body with conditions unlike anything in our solar system. These proponents emphasize that while extraordinary, the comet might still fit within the bounds of natural astrophysical processes that have yet to be fully understood. On the other side, some scientists cautiously raise the possibility of artificial or engineered origins. The sharp 7.2-hour light curve, mechanical-like acceleration, and precise, repetitive patterns are difficult to reconcile with known natural behaviors of interstellar objects. These features, combined with the extreme chemical composition, evoke comparisons to Oumuamua, the first well-studied interstellar visitor, which also exhibited acceleration without obvious cometary outgassing. Such recurring anomalies suggest that these objects might not all conform to conventional models, prompting questions that skirt the boundary between astrophysics and speculative engineering hypotheses. The debate has spilled into peer-reviewed preprints, open-access archives, and social media forums, with astronomers worldwide scrutinizing every piece of data. Each new observation, whether spectral line, photometric curve, or acceleration measurement, forces a reassessment of the models, and no consensus has yet emerged. Some caution against jumping to conclusions, recalling the prolonged debates over Oumuamua, which, despite years of analysis, left critical questions unresolved. Others argue that ignoring the possibility of artificial origins limits the scope of inquiry in a situation where the natural explanations are already stretched to extremes. Amid the controversy, NASA's Planetary Defense Office quietly categorized 3I Atlas as a high anomaly object. While not a threat to Earth, its unpredictable behavior and unique properties place it in a special category reserved for objects that challenge conventional understanding. Internal discussions track it meticulously, noting that extraordinary claims require extraordinary evidence. But even the most skeptical voices admit that this interstellar visitor is rewriting the known rules for cometary and interstellar phenomena. Ultimately, 3I Atlas has become a focal point for examining the boundaries of natural cosmic processes. Its unusual properties force scientists to confront questions about the diversity of planetary systems, the potential for unknown physical mechanisms, and the rare possibility of engineered artifacts in space. The debate is ongoing, reflecting both the excitement and the uncertainty inherent in encountering something completely unlike anything humanity has observed before. NASA has officially classified 3I Atlas as a high anomaly object, acknowledging that it defies conventional categorization. Despite intensive observation campaigns, its extraordinary chemical composition, with carbon dioxide vastly outpacing water and nickel dominating while iron is nearly absent, remains unexplained by current cometary models. The comet's dynamic behavior, including erratic acceleration and subtle trajectory jitters, adds further complexity, indicating forces or mechanisms beyond standard gravitational and outgassing processes. Photometric data only deepens the mystery. The precise 7.2-hour periodic brightening behaves unlike any known comet, suggesting an almost mechanical regularity in its rotation or structure. Attempts to model the light curve through natural shapes, tumbling, or reflective surfaces have failed to fully explain the observed consistency, leaving open the possibility of either an unknown natural process or, cautiously, engineered features. The combination of chemical, physical, and photometric anomalies makes 3I Atlas one of the most perplexing interstellar visitors ever recorded. While scientists continue to gather data and cross-check observations from JWST, ground-based telescopes, and other instruments, no definitive explanation has emerged. Peer-reviewed studies, preprints, and open-access archives reflect ongoing debates, with some emphasizing exotic natural formation scenarios and others noting the uncanny. Parallels to prior interstellar anomalies like Oumuamua, the official designation as a high anomaly object, underscores the uncertainty surrounding 3I Atlas. It is not considered a threat, but it represents a scientific wildcard, forcing experts to reconsider fundamental assumptions about the diversity of interstellar bodies, planetary system formation, and the possible limits of natural processes. Until further observations are made, the true nature of 3I Atlas, whether it is a cosmic fluke, Kotofidanthauerns Naasi Chand, a messenger from an alien chemical environment, or something deliberately engineered, remains an open question, preserving both the wonder and the caution that come with exploring the unknown reaches of the universe. The story of 3I Atlas is far from over. Each new observation peels back another layer of mystery, revealing a cosmic visitor that challenges everything we thought we knew about interstellar objects. Its unusual chemistry, erratic motion, and mechanical-like light curve hint at forces and processes beyond our current understanding, keeping scientists, historians, and enthusiasts alike on the edge of discovery. As telescopes continue to track its journey through the solar system, every spectral line and every flicker of light becomes a clue to its origin. Whether a product of exotic natural processes, A messenger from a distant star system, or something more deliberate. Rethinking, Atlas reminds us that the universe is far stranger and far more wondrous than we can imagine. For now, we watch, we measure, and we wonder, knowing that each revelation brings us closer to understanding not just this singular visitor, but the vast, untamed possibilities that lie beyond our solar neighborhood. The cosmos has thrown down a challenge, and humanity is only beginning to answer. What if everything you've been told about the moon is a lie? When renowned physicist Michio Kaku broke down in tears during his presentation at a major space science symposium in Geneva, the room fell silent. The man who has spent decades explaining the mysteries of the universe to millions was visibly shaken by what he was about to reveal. The data he presented that day didn't just challenge our understanding of the moon, it shattered it completely. Quantum deep imaging satellites, subsurface radar, and gravitational lensing technology had uncovered something so shocking that multiple international agencies verified the findings before Kaku was authorized to speak. What they found beneath the lunar surface defies everything we thought we knew about natural celestial formation. It began in Geneva, at one of the most anticipated gatherings of scientists, astronomers, and futurists from around the globe. The symposium was known for unveiling bold theories and new discoveries, but this year, anticipation carried an unusual weight. When Michio Kaku, the world-renowned theoretical physicist and futurist, walked onto the stage, the room fell into a silence that was more than just respect. It was curiosity mixed with unease. Kaku had built his reputation on being a bridge between hard science and visionary speculation. He could talk about string theory one moment and humanity's future among the stars the next. Audiences expected imagination from him, but they also expected clarity and evidence. Yet that morning in Geneva, his demeanor was different. There was no playful humor in his eyes, no casual warmth in his gestures. Instead, he carried himself with a kind of solemn urgency, as if the information he was about to reveal weighed heavily on his shoulders. The title of his presentation, displayed across a vast screen, read, "The Moon, a Paradigm Shift in Understanding." The words alone stirred murmurs among the crowd. Most had expected the talk to cover well-worn territory, perhaps updates on lunar colonization plans, NASA's Artemis program, or speculative ideas about mining lunar resources. Some even assumed it might be a futuristic pitch about using the moon as a launching base for Mars missions. But Kaku's voice, steady yet unusually subdued, quickly shattered those expectations. He began by reminding the audience of the moon's place in human imagination, how every civilization had looked up at it with reverence, woven it into myths, and used it to mark time. But then he paused and with a quiet intensity said, "What we thought we knew about the moon is about to change." The room shifted. Scientists who had come prepared to take notes on orbital mechanics or colonization strategies now leaned forward with furrowed brows. This was not going to be another technical update. This was going to challenge the very foundation of how humanity understood its closest celestial neighbor. Kaku explained that the findings he was about to share were not his alone. They were the product of an unprecedented collaboration between space agencies in Europe, Asia, and beyond. These agencies had recently deployed a new generation of satellites equipped with quantum deep imaging systems, gravitational lensing, arrays, and radar capable of penetrating beneath the lunar surface with greater precision than ever before. The data, he said, did not just fill in gaps in our understanding, it tore open the framework entirely. As he spoke, images began to appear. Behind him, high-resolution scans of the moon, patterns and colors highlighting areas that most of the world had never seen. He let the images linger in silence, as though giving the audience time to prepare themselves. Then, With deliberate pacing, he delivered the statement that would ripple far beyond that auditorium. The moon may not be what we think it is. Gasps and whispers spread through the hall. This was no longer just a presentation. It was a revelation. Kaku, usually so animated in his delivery, stood motionless, his voice steady, his eyes fixed on the audience as though measuring their reactions. It was the beginning of a story that would leave the scientific world and the public at large forever changed. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. After his startling introduction, Michio Kaku shifted the audience's attention to the cutting-edge technology that had made these revelations possible. He explained that for decades, the moon had been studied with telescopes, orbiters, and seismic data from the Apollo missions, but all of those tools had provided only a partial picture. The moon, for all its familiarity, remained a mystery. That mystery began to unravel with the deployment of a new generation of instruments, machines so precise that they seemed almost futuristic in their capabilities. These were not the old radar sweeps or grainy photographs. These were quantum deep imaging satellites, able to bend the very fabric of space-time through gravitational lensing to reveal what lay hidden beneath the surface. They were paired with subsurface radar systems capable of probing hundreds of kilometers deep into the lunar crust, mapping structures that had never been seen before. The project was unprecedented in scope. Agencies from Europe, Asia, and smaller spacefaring nations pooled resources, sharing data rather than competing. For the first time, humanity had eyes that could see the moon not as a flat, cratered sphere of dust and rock, but as a layered object with secrets buried far beneath its surface. Kaku described the findings slowly, letting the weight of each word settle over the audience. At first, the data seemed routine: density maps, heat signatures, gravitational fluctuations. But, as the analysis progressed, the results defied every conventional model of lunar formation. The moon's internal density readings were inconsistent, not the gradual, natural layering one would expect from a body formed in a cosmic collision, but sharp disparities, voids where solid rock should have been. Some cavities stretched for hundreds of kilometers, too vast to be dismissed as volcanic tubes or natural hollows. Even more unsettling was their arrangement: symmetrical, repeating, evenly spaced, as though laid out according to a plan. The images on the screen behind Kaku began to change. Grainy radar scans gave way to clean, geometric outlines glowing against the blackness of space. Structures, grids, and what looked like corridors of emptiness threaded through the moon's interior. The auditorium grew tense. Scientists who had dismissed such ideas as fringe speculation now sat frozen, confronted with evidence that could not be ignored. Kaku added another layer. The scans had revealed reflective materials buried deep under the lunar regolith, alloys that gleamed unnaturally in thermal and radar imagery. These were not random deposits of ore. They reflected energy in ways that hinted at engineered surfaces, like panels or casings, preserved under billions of years of dust and impact. He explained that these anomalies weren't isolated. Taken together, the cavities, the geometry, the reflective layers, and the density irregularities painted a picture that no current model of lunar evolution could account for. "This is not the moon we thought we knew," he said gravely. The room was silent, save for the occasional rustle of paper or hurried scribbling of notes. The air seemed charged, as though every person present understood they were witnessing a moment in history. Humanity had stared at the moon for millennia, written poems to it, worshipped it, and studied it. But for the first time, science was beginning to peel back its skin, and what it revealed was something utterly unexpected. As the audience sat in silence, Kaku advanced to the next sequence of findings. This was where the data stopped being unusual and began becoming impossible to dismiss. On the giant screen behind him, scans of the moon's interior revealed a startling truth. The satellite that humanity had always considered a natural companion was not behaving like one at all. The first anomaly was sheer scale. Within the moon's body, researchers had discovered vast internal cavities, hollows stretching hundreds of kilometers in length. Natural explanations such as lava tubes or collapsed voids had been considered, but these cavities were different. They were too vast, too consistent, and they appeared not as chaotic tunnels, but as ordered chambers spread in regular patterns across multiple regions. It was as if someone had hollowed out enormous portions of the moon with deliberate precision. Kaku paused on one image that drew collective gasps. It showed cavities aligned in a near-perfect grid, each separated by similar distances, forming something more like an architectural blueprint than a geological accident. This was not randomness. This was geometry on a planetary scale. The second anomaly deepened the unease. Within these cavities, radar and thermal imaging detected faint reflections that did not belong. Scientists had long understood the lunar regolith, dust and rock billions of years old, was a chaotic mixture of debris from countless impacts. But these reflections suggested the presence of metallic alloys buried far beneath the surface. Alloys arranged not in veins or scattered patches, but in flat, uniform planes. Kaku explained that these reflective signatures resembled the smooth surfaces of engineered structures, plates, casings, or perhaps shells, designed to endure eons of bombardment. Their consistency across multiple regions hinted at a system, a pattern of design. They were not random minerals born of cosmic chance, but evidence of construction. The third anomaly tied everything together. As researchers mapped the cavities and alloys, they noticed that many of the geometric formations intersected cleanly, like beams meeting at right angles or panels overlapping along straight lines. These were shapes foreign to natural geology, but deeply familiar to human eyes. The shapes of design, the signatures of architecture. Behind Kaku, the screen lit up with enhanced images, glowing outlines of honeycomb-like grids, faint but unmistakable. The crowd's silence deepened into something heavier, more electric. The evidence was no longer just statistical irregularities or unexplained signals. It was visual, undeniable. This, Kaku said, pointing to the glowing grid, is not what we expect from nature. These are the hallmarks of design. His beauty voice carried a gravity that matched the revelation itself. He did not rush, did not embellish. He simply presented the data and let the images speak for themselves. Some scientists shifted uncomfortably in their seats. Others scribbled furiously in their notebooks. A few simply stared at the screen, wide-eyed, unable to look away. The seeker realization was setting in. If these anomalies were real, then the moon was not simply a rock captured by Earth's gravity. It was something else, something engineered, constructed, or at the very least, altered by intelligence far beyond our comprehension. For the first time in human history, the moon was no longer just a celestial neighbor. It was a question mark carved into the night sky, and with every image Kaku revealed, that question grew larger. If the vast cavities and geometric structures suggested that the moon's interior was engineered, what came next hinted at something even more unsettling, that parts of it might still be active. Kaku advanced to the next slide, and a new series of images filled the screen. These were thermal maps of the lunar interior, captured by deep penetrating sensors orbiting high above the surface. At first glance, the moon appeared as one would expect, cold, inert, a lifeless body drifting through space. But scattered across certain regions were faint yet undeniable heat signatures pulsing softly against the backdrop of darkness. These emissions were not random. They were concentrated around the same internal cavities and reflective planes previously identified. They radiated in steady, measured patterns, nothing like the chaotic release of geothermal activity. And most striking of all, Their profiles matched something deeply familiar to scientists on Earth. The heat signatures resembled reactor cores, the kind used in nuclear power plants, only on a much grander and older scale. Kaku's voice carried a deliberate calm as he explained the implications. "We are not seeing volcanic remnants," he said. "We are not seeing natural geothermal processes. What we are detecting is energy, contained, regulated, and persisting far longer than any natural source could account for." The data had been cross-verified by multiple agencies, each using independent instruments and calibration methods. There was no doubt about its authenticity. The Moon, a body long believed to be geologically dead, was still emitting heat from within. But it was not the heat of magma or tectonic friction. It was the faint, rhythmic glow of something designed to endure. The audience shifted, the weight of the revelation pressing heavily over them. The thought was almost too much to process. Not only might the Moon have been engineered, but the systems inside it could still be dormant machines, remnants of a technology that predated human history by billions of years. On the screen, a time-lapse sequence began. Over the course of months of monitoring, the thermal signatures flared and dimmed in quiet cycle, as though the Moon itself was breathing. Each pulse radiated outward with uncanny precision, like a beacon that had been running silently since deep time, long before Earth's first civilizations looked up and named it. Kaku let the sequence play out in silence before he spoke again. "If these are reactors, or some form of energy generators, then the Moon is not simply a relic. It is an artifact, and artifacts are made." The statement landed with a heaviness that words rarely achieve. Some in the room leaned back, as though physically resisting the idea. Others leaned forward, transfixed, unable to break their gaze from the evidence before them. The possibility was staggering. Somewhere deep inside the Moon, technology older than humanity might still be functioning, perhaps waiting, perhaps maintaining something unseen. In that moment, the Moon was no longer just a silent rock orbiting Earth. It was alive, not with biology, but with energy, with purpose, with a quiet hum that had gone unnoticed until now. As the revelations deepened, Michio Kaku turned to one of the most baffling discoveries of all: the Moon's gravity. For decades, lunar missions had puzzled over the so-called mascons, or mass concentrations, strange regions of unexpectedly strong gravity hidden beneath certain craters. They were odd,